So, good morning student. Today I will discuss a specific topic related to chemical kinetics, and because we have already performed some chemical kinetic experiments. So, for example, you have studied the hydrolysis of methyl acetate. You have studied saponification of ethyl acetate, which is a second order reaction. And in future, you will study the potassium persulfate Ki reactions, which is also a second order reaction. Now suppose you want to see effect of some inert electrolytes on those reactions. Suppose you are using one univalent electrolyte like potassium chloride, or you are using sometimes bivalent electrolytes, or sometimes you use bivalent electrolytes. So then question arises, what would be the possible effect of these electrolytes on rate constant of a chemical reactions? And such type of effect is known as ionic strength effect, or sometimes it is called as kinetic salt effect. Now, because when you are using any electrolytes, it will dissociate and forms different ions, and the concentration of your electrolyte may be different. It may be 1 molar, it may be 2 molar, it may be 0.05 molar, but it will dissociate in different ions. So I can call it is the effect of electrolytes on the rate of chemical reactions. That means that particular ions, suppose potassium ion K plus, chloride ion chloride minus, sulfate -2, perchlorate, like that, nitrate. So that charge species definitely affect the activated complex. So how do we study all those type of the effect? So that is actually called effect of electrolytes, or sometimes you can call it is salt effect. Now there are, just I have already written univalent, like if I write univalent, generally we use KCl. Bivalent, K2SO4, like that. There may be so many examples. Or bivalent, suppose magnesium sulfate. I am just giving one example. And suppose it is 1 molar, it is also 1 molar, and it dissociates potassium ion as well as the chloride ion. So such type of effect is known as the salt effect, and salt effect can be divided into two parts. One is called primary salt effect, and second is the called secondary salt effect. I will explain what is primary salt effect and what is secondary salt effect. And sometimes the equation which is responsible for such type of salt effect, that means if you know that equation, you can predict what would be the possible effect of the electrolytes, and that equation is very important in the chemistry. That is called Bronsted-Bjerrum equation. Sometimes it is called Bronsted-Bjerrum equation. So either you can call it as a primary salt effect or secondary salt effect, or derivation of Bronsted-Bjerrum equation. Why it is called Bronsted-Bjerrum equation? Because you all know regarding the Bronsted is a very well-known chemist. So Bronsted and Bjerrum actually derived this equation long back, I think 1922. So therefore it is called Bronsted-Bjerrum equation. Now let me explain what is primary salt effect and what is secondary salt effect. Suppose I am using a system A plus B is converted into C, of course through activated complex. Suppose the potassium persulfate K2H2OH and Ki reaction, and you are using potassium chloride, different types of. So if it is a primary salt effect, that ions directly affect the activity coefficient. Whereas if it is a secondary salt effect, that electrolytes directly affect the actual concentration. Suppose I am using a weak acid and it dissociates in hydrogen ion, and so that electrolyte directly affect this concentration of that species. That is called secondary salt effect. But in this lecture today I will concentrate only on primary salt effect and Bronsted-Bjerrum equation. I have already told you that primary salt effect means influence of electrolyte concentration on the activity coefficient and hence rate of the reaction. You might have heard about the activity and activity coefficient, which is very, very important terminology in electrochemistry, because if I want to write the activity, it is related to the stoichiometric concentration and activity coefficient. Now it is up to you that you can write activity coefficient F or gamma, whatever it is. So absolutely no problem. So naturally it is related to the concentration. But if it is a secondary salt effect, change in the concentration of the reacting ions on the addition of the electrolytes. So that is secondary salt effect. Now I am giving some very common example which you have already performed in your practical classes. Let me start this hydrolysis of the methyl acetate, and naturally this is a neutral species and this is a positively charged species. Similarly, if I am taking the saponification, this is a neutral species and this is a negatively charged species. If I am using this potassium persulfate and Ki reactions, it is negatively charged, it is also negatively charged, so it is resulting is plus. So what happened when you perform the experiment in the presence of electrolyte and in the absence of electrolyte? We have observed that when you plot a graph between log of rate constant and suppose under root of I'll tell you the ionic strength because that is also very important concept. Ionic strength. I'll explain because unless until you know the concept of the ionic strength, it is very difficult for you to understand the primary salt effect. I am just giving a very simple example that I am taking this, you have already performed this. Suppose I ask you to add potassium chloride or any other electrolytes and see the effect of salt or electrolyte. What happened? Fortunately or unfortunately, I will explain why such things happen. When you plot a graph between log of K observed and different concentration of KCl, in the case of methyl acetate hydrolysis, there is no effect. Why? And whereas in this reaction, you are using the potassium persulfate and Ki, and you are using different KCl solution, you will see that rate of reaction is increases. So in one case, there is no change in rate constant with respect to ionic strength, and in one case, rate of reaction increases. In some cases, and even also in hydrolysis of methyl acetate also, there is no change. And in some other reactions, I am giving this example. So you are getting three types of observation. In one case, there is no change. In one case, with respect to ionic strength, rate of reaction increases, and in one case, rate of reaction decreases. That means now the role of primary salt effect and Bronsted-Bjerrum equation. If you understand the Bronsted-Bjerrum equation, you can predict the effect of electrolytes on the chemical reaction. That is the objective of this primary salt effect or the secondary salt effect. Now in this example, here if I plot a graph, again log of K or K0, whatever it is, and under root of mu, in the second case, because it is positively charged, it is negatively charged, so valence is, so here I am getting rate constant decreases, whereas this constant increases. So that can be explained with the help of Bronsted-Bjerrum equation. And if you ask me, sir, what is the final formula of Bronsted equation, I must tell you that I will derive it, but you must know. So from where log of K, that means rate constant in the presence of electrolyte, log of K0, rate constant in the absence of electrolyte, plus 1.02 approximately ZA ZB under root of mu. Mu is called ionic strength. So I am plotting this log K by K0 under root of mu. So this is actually our slope value. So that means now you can understand ZA is the valency of this plus and minus, plus and minus is minus. ZA ZB value is negative. In some cases ZA ZB value is positive. And if one molecule is neutral, so ZA/ZB value is 0. So that is the output of the Bronsted-Bjerrum equation. But let me explain all these things. Now, before going into details of the primary salt effect and Bronsted equation, it is necessary to know the concept of ionic strength. Sometimes in some books it is written like I is also you can write, or in mu is also written, that is called the ionic strength. It is very simple. And very important for the examination also. It is very simple, and the great scientist Professor G.N. Lewis and M. Randall developed. Don't forget this concept. It is a very, very useful concept for whole chemistry. Without knowing the ionic strength, you can't calculate the strength and the concentration, valency and other things. So it is very simple. Half summation Ci Zi square. C means the concentration of the ions. Suppose I am using 1 molar KCl. Okay, I am using 1 molar KCl. So C is the concentration, Z is the valency. So I should write half 1, valency is 1, so 1 square for potassium ion. Then for chloride ion, concentration is 1 square. So 1 square 1 plus 1 is equal to 2 divided by 2. What is the ionic strength? 1. Very good. So it is a thumb rule also. That means for univalent electrolyte, the concentration is equal to ionic strength. You need not to be worried. You need not to be calculate. Suppose I am giving point objective type question, MCQ. Point, what is the ionic strength of 0.5 m KCl? You have to write 0.05. You can calculate it. You follow my point? So for univalent electrolyte, it is same. So like bivalent, it is 3 times then univalent. Bivalent, it is 4 times then. I will explain gradually. Suppose a solution contains 0.05 KCl, 0.05 NaCl, 0.03 lithium chloride. So you have to calculate each and every ion. Don't write minus or plus, just valency, that's enough. So if it is 1 is concentration, if it is 2, so 2. So don't write -1 or -2. Okay. So this is, so you have to calculate the concentration of sodium ion as well as the chloride ion, potassium ion or nitrate ion, all these, lithium ion and lithium perchlorate suppose. So if a solution contains large number of ions and different types of the concentration, so you have to calculate all the ions. So this is called the ionic strength. It is a very important in your, for electrochemistry part is also there, ionic strength, as well as the physical chemistry ionic strength, that is called the ionic strength. Because whenever you add some KCl, so you must calculate the actual strength of that electrolyte, and with the help of this formula half Ci Zi square, we can calculate the strength. Okay. Now, as I told you, the rules. For univalent, the ionic strength is equal to the concentration. Bivalent, Suppose 2 K2SO4, 2 into 1 square plus valency is 2. You follow my point? Why I am taking 2? Because 2 potassium plus sulfate CI square. C concentration is 1, suppose. So 2, 4, total 6, half is equal to 3. So for uni-bivalent, suppose there are 0.01 molar K2SO4. Calculate the ionic strength. It will be 0.03 molar. Again, it is an objective type question. Similarly, for bivalent electrolyte, the ionic strength is 4m. So by that method, you can calculate the ionic strength of any solutions. Now I am just derivation of. Now let me derive the Bronsted-Bjerrum equation. Okay, so I am coming to derivation. Bronsted-Bjerrum equation. Very simple. And of course, today I am doing primary salt effect. Primary salt effect. Okay, so you can see it there. Primary salt effect. A plus B is equal to X activated complex, or you can write, and this is the product. This is the first step, and then conversion of activated complex is the slow step. So as normal case, rate of the rate determining step, suppose this is some K activated. It is up to you, whatever you write. So K activated is equal to this concentration of X. This is activated complex. And we are using different types of potassium ion. So it will affect the activity coefficient of this species. And normal cases, we are using K observed is equal to, it depends upon A and B. If it is a second order reaction, potassium persulfate, K2S2OH and Ki reaction. This is the objective. So what I have to do, just like your normal cases, because it is a slow step, rate determining step, so I have to substitute the value of x here. Then I will get the final result. So if I write k is equal to capital K, this is not rate constant. Rate constant is here. This is k. This is related to x, activity of x, activity of A, and activity of B. I think you have already studied in electrochemistry the activity coefficient, mean ionic activity, which is very important concept in chemistry. So it is activity. So now one thing is very important. Whenever you study the effect of electrolytes, the most important point is that you must consider the solubility of that electrolyte, because sometimes what happens if your concentration of electrolyte is high, there is a solubility problem. So basically, when Bronsted and Bjerrum determine this primary salt, they generally consider dilute type of solutions, because if your KCl solution is higher concentration, then of course we have to modify that equation. That was determined by Macaulay. So therefore there is another equation, Bronsted and Macaulay and Lamar. I will not explain today this modification of this Bronsted-Bjerrum equation. I am considering that the solubility is okay, and it is a dilute electrolyte solution. I think less than 1.05, 0.04, 0.03, like that. Okay. So that we can write activity is equal to, actually, I have already told you, the stoichiometric concentration and activity coefficient. Now this is very important. Activity coefficient. Activity coefficient. Therefore, I have brought a book of electrochemistry. Although I am just studying you the kinetics. Today, what I am doing? I am doing the kinetics, primary salt effect. But you have seen that I have brought a book, An Introduction of the Electrochemistry by Glaston. This is a very famous book. Why? Because I have to refer some electrochemical concept for solving the Bronsted equation. Therefore, I have brought this book, Glaston. You will explain. You will understand why I am talking about the electrochemistry concept, because the question of ions, question of activity coefficient, and other things. So you can write it is a molar concentration of X and activity coefficient of X. You can write like X or whatever it is up to you. F of A or F A, and B is also there, and F of, so I can slide A, B, like that. So I have to calculate the X. So therefore X is equal to K, capital K, A, B, isn't it? Activity of FA, FB divided by, you can write that or like that, X, you can write that. So now what you will do? We will substitute the value of X, concentration of activated complex, to our slow reactions. So I will erase all these things. So therefore rate is equal to, I think make it air condition 22 or 25. Temperature is very high. 22, 23. So anyway, rate is equal to this, then K. Follow my point? It's very simple. AB, isn't it? F, activity coefficient of A, activity coefficient of B, and F, like that. Okay? This is in rate, and in one case rate is equal to K observed, this. So this, so K observed is equal to, now this K and K dash, suppose this is equal to K0. Suppose FA, FB, F activity. So there is a red color. Now I am asking this question to you. The student can reply my question, that Bronsted and Bjerrum derive a simple equation which relates the observed rate constant is equal to K0, but this I just have written some constant. Then activity coefficient of F, activity coefficient of B, two species, persulfate and I, and there is activated complex. So this. So how do you solve further? Anybody? Because we have already studied the electrochemistry. This is not the final equation of primary salt effect or Bronsted-Bjerrum equation. What is the final equation? I have already given you the information. Log K is equal to log K0, then 1.02 ZA, ZB, and under root of mu, right? So, so how do we get that equation? So Bronsted was waiting that how do we solve that equation. In the year of 1921 or 1922, a great scientist, he is a Nobel laureate, and his name is Peter Debye. You know Debye, Peter Debye, and that time, I think in 1924, Debye and his collaborator Hückel, they formulated a wonderful equations that is called Debye-Hückel limiting law, which relates the concentration of that electrolytes or valency and other things with activity coefficient. Because in order to derive this Bronsted-Bjerrum equation, we need a equation, because we are using potassium chloride or different types of the electrolytes. So now we wish to study the role of that particular ions on that activity coefficient. So this formula is not sufficient, so we need some extra or additional relation which can relate the activity coefficient and valency or whatever the concentration of the ions. So thanks to great Debye-Hückel. So therefore, we will take the Debye-Hückel limiting law Any idea about this equation? Anybody in the class? What is Debye-Hückel? I am not talking about the Debye-Hückel-Onsager equation. These are all related. There are three concepts. Debye-Hückel-Onsager equation is different. I am talking about the Debye-Hückel limiting law, which relates activity coefficient and valency and other things, and that is log of, just remember, very important in electrochemistry, log of F is equal to minus Q ZA or ZB or ZZ under root of mu or I in ionic strength. This is called Debye-Hückel limiting law. And yes, this is F, it is valency, this is half CI square, everything is there. So let me show you that great formula which is called the Debye-Hückel limiting law. Yes. Now this is a great formula proposed by the Debye and Hückel, and this is log of activity coefficient, whatever it is, mean activity coefficient, So you just adjust it. So I can write like that, log of F, whatever it is, same thing, minus, I have written here Q. Q is a constant. You can write A also. Z, because if I am talking potassium ion and chloride ion, so Z plus, Z negative, under root of half means same thing, mu. You can write here A also, no problem, it is a constant. Here you can also write I, ionic strength, no problem. And what about the Q or constant? So it is sometimes related to thickness of ionic atmosphere. So the Q is equal to N square, N is the Avogadro number, charge of electron, 2 pi half 2.303 epsilon kT 3 by 2 1000 half. If you want to learn these details about this Debye-Hückel theory and the what is Q, and it is a constant. You just when you derive the Debye-Hückel limiting law or Debye-Hückel-Onsager equation, you have to explain this thickness of ionic atmosphere, everything. But when you derive the primary salt effect or Bronsted-Bjerrum equation, you just write that Q is a constant value. But of course, because medium is very important, medium, temperature is also very important. Suppose your reaction, both the reactants are not soluble in water, then you have to use some mixed solvent like dioxin and other things. So you know that the dielectric constant of water is different, 72 or like that. Dielectric constant of dimethyl sulfoxide is different. So you just, if you don't want to remember it, forget it. But it is available in the books of Glaston. What is the value of Q? How you get this value of Q? In Avogadro number, E, and this epsilon is the dielectric constant. K is the Boltzmann constant, T is the temperature. So for, just you remember, for water, the aqueous medium, and room temperature, the value of Q is equal to 0.509 approximately for water. Don't worry about the derivation of Debye-Hückel limiting law or Debye-Hückel Onsager theory, thickness of ionic atmosphere. No, you just, but you have to write this equation that there is a relationship between activity coefficient and concentration, that is log of F is equal to minus Q Z plus Z minus under root of mu, and Q is equal to at room temperature for water, it is approximately 509. That's all. Okay. Now what you have to do? Now you know the Debye-Hückel limiting law. Now you have to substitute, or with the use of Debye-Hückel limiting law you can explain these things. Is it clear? So now let me rub all these things, and I am concentrate only on this part. So right. So I am getting the value. So it will take only 2 minutes. Log of F, our system, minus Q Z plus or ZA or Z minus, you can write, under root of, this is Debye-Hückel limiting law. And what was our formula? K is equal to K observed, K0, then FA, FB, okay. That was our formula. So taking logarithm, so log of K observed, or K you can write, log of K0 plus log of FA plus log of FB minus log of okay. So for we can write first, I will write log of FA minus Q, here ZA, valency of that particular ion, suppose potassium ion, then under root of mu, then for B, log of FB, negative ion, persulfate, or KCl minus Q ZB under root of mu. Then last, log of, you can write natural log also, F activated. Red color is visible, okay. So I'll just change it, otherwise minus Q. Now here there are, because it is activated complex consists of both the things. So it is ZA plus Z. I think log of what is the, just a minute. Z is it, which okay. So Z is it. Z is it, so J, I think Z square. Z square. Because both the ions are under root of. Now substitute all these values in this equation. So log of K0. Now in place of log of Fa minus Q Z square under root of mu, again minus, because plus log of Fb, so minus Q ZB square under root of mu. Here it is minus, so therefore plus Q ZA plus ZB square under root of mu. Why it is plus? Because here is minus log F. So this part is common. So what I do, log of K by K0, just doing shortcut. Or you can write log K minus log K0, same thing, minus Q under root of minus Q. So Z square, ZB square. Now what we will do, because it is, here it is plus, so minus, you can call it ZA plus ZB square. So what I can write, Z square plus ZB square plus 2ZA ZB. A plus B square, Z square, ZB square plus 2Z minus. So we'll change the sign. So this will cancel with this will cancel with this cancel with this. So this minus and this minus. So what we will get? Log of K divided by K0 is equal to, so here is also minus, here is also minus, so 2Q, why 2? This 2, this ZA cancel with this ZA cancel with this, ZA ZB under root of mu is common. This is called Bronsted-Bjerrum equation, and Q is equal to 0.509. So, or 51 approximately. See, if we multiply it with this Q, so it is equal to 1.02 ZA ZB under root of mu. Log of K by K0 is equal to 1 approximately 1.02 ZA ZB under root of mu. Now if it is y, K by K0 is y and mu is x. Log of K and K0. K is the observed rate constant in the presence of electrolyte. K0 is the log of rate constant in the absence of the electrolyte. And under root of mu. Just y is equal to straight line equation mx plus c. Y is this, x is this. So what would be the slope? ZA ZB. ZA ZB is the slope. Now how do we predict? Now this equation is called the Bronsted-Bjerrum equation. So how do you predict? Suppose you are doing, again I am saying the same old example, that potassium persulfate and Ki reaction. Ethyl acetate and OH reaction. So in case number A, what would be the value of ZA and ZB? Case number A, minus negative 2 negative into minus 1 negative. What should be the value of ZA ZB? Anybody? Positive. So you can predict that rates increase. What would be the? It is 0, it is minus, it is 0. So no effect. Suppose in some cases one is positive, another is the negative, suppose. So what would be the value of ZA and ZB? Slope value negative. So ZA ZB 0, ZA ZB positive, ZA ZB negative. So it is one type of prediction. That means suppose you are performing some of the experiments. You are performing some of the experiment and you know the species. So before doing of the experiment, ultimately you have to depends on your result. You perform the persulfate iodide in the absence of electrolyte. Experiment number 1. Experiment number 2, you add 1 molar KCl. Experiment number 2, you add 2 molar KCl. Experiment number 3, you add 3 molar KCl. So you are changing the ionic strength also. You are changing the ionic strength also, and it is a univalent. So mu is equal to 1, 2 and 3. So suppose here 3 point, this is 1, suppose this is 2, so 3. So you can predict with the help of Bronsted-Bjerrum equation. So lastly I am giving some of the example so that you can understand. So you just, same thing I have just written here. First case Z square, second ZB square, and this is the ZB square. It's also same thing. You can write F in place of F, you can write gamma, no problem. In place of activated complex, you can use the star. It is up to you. So it has no, in place of mu, you can write I. So that is not a problem. Yes, now I have already written the formula and I have taken this book from Ladler. So now you predict. Very good books. This is the formula log K, log K0, 1.02 ZA, ZB under root of mu. So suppose I am taking this example. Ferric 3 plus. Or ferrous maybe. So 2 plus is minus 3. So is equal to minus 6. So the rate will decrease. Then again this is this case plus 2 and minus. Net result is negative, minus 2. So again decrease. Here it is negative, here it is 0. So net result is 0. Here it is 0. So 0, no change. Here negative, then negative, plus. So here 2 negative, 1 negative, plus 2. So again 2 positive, 2 positive, 2 into 2 is 4. So it will increase. So there is a possibility of MCQ question, and they can give the large number of examples and ask you that write the possible effect of ionic strength on different reactions. And all these reactions are available in the book of Ladler. Although I am using very old edition, but even in your new edition also, it is a very old edition book, because that time diagram was clear, so I have taken from that book. But even in new edition also, you will have all these examples. So you must write all such type of the examples. And if you see this one question paper, just 1 minute, so that you can understand the importance of this type of reaction. Yes. What is the effect of increasing ionic strength using KCl on the rate of following second order reactions? S2O8, 3I, 2SO4I3, increase, no effect, decrease, first increase, then decrease. So you have to write the correct things. So because in this case, the rate, you see, rate of reaction increases, because negative, negative, positive, 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 negative, positive, 0, like that, ion dipole type of reaction. But it is Bronsted-Bjerrum equation. Not, and it is again suitable for the dilute solution, for concentrated solution, there is some modification. So very slight. Today I will not discuss this modification. That is slightly different. That is log of f is equal to same thing, minus q under root of z. Sorry, not under root of z. ZA ZB under root of mu plus one additional term is there, that is called the B mu. I will not discuss today B mu. So that is called the modified Bronsted equation, Macaulay equation, and it is again for some. And why we use this equation? Because in particular that type of case, and there is no change. Ion dipole type of the reactions. If it is ion dipole type of the reaction, so whatever the value of ZA is exactly value of the activated complex, because that one molecule has no charge. So for that we will use the Macaulay equation. Sometime in examination there is a possibility of question of that Macaulay equation, but don't worry for that Macaulay equation. And in next class I will discuss the secondary salt effect, which is very simple. But today, now let me summarize that today I have discussed one of the simplest equation, that is effect of electrolytes on a chemical reactions. And there are two effects, primary salt effect and secondary salt effect. But today I have derived the primary salt effect. That means whatever the ions that will directly affect the activity coefficient of the species. And that equation which is responsible for this thing, that is called the Bronsted-Bjerrum equation. And on the basis of the Bronsted-Bjerrum equation, we can predict that yes, if we increase the concentration of cases, there is a possibility of the increase, because we know the equation. Log of K divided by K0 is equal to 1.02 under root of mu and ZA and ZB. ZA and ZB is the slope value. Thank you very much.